Good morning, everybody. So this is the last class, and what I'm going to talk about is something we already mentioned several times, is a question of vectorization of persistent diagram, or vector representation of persistent diagram. Maybe before we start, do you have any question about what we did yesterday? Okay. In fact, we have already discussed a little bit this question of so the idea is that when you get a persistent diagram, so you start from some data, you build a filtration on top of your data, or in some way you get some filtration, you compute a persistent diagram, and you can see this persistent diagram as some kind of topological feature, topological information about your data, right? And what we have seen is that this persistent diagram is just a set of points in the plane, in general, a finite set of points, and it is not well suited to be used for further classical machine learning tasks, such as regression or classification, because most of the existing algorithms need to be fed with vectors, objects that are living in vector spaces. So we have seen, so now the question, and this is quite an active research area, is that how can we, general question is that how can we convert a persistent diagram into a vector in a clever way, in which by this I mean that in a way that we don't lose the interesting or important topological information we get in this from our data in this persistent diagram. So we have already seen some ways to do that. For example, yesterday we have been talking a lot about persistence landscapes. We have seen that this is a way to convert a persistent diagram into a function or into an element of a functional space. And that has some very nice theoretical properties that preserve the stability properties, etc., etc. Okay, so this was an example we already discussed. And another example we have been discussing a little bit are Betti curves, where you convert your persistent diagram into Betti curves. It's another way to convert your persistent diagram into a function, right? And this is another vectorization. So when we did this, we did this in a way. All these methods are methods to vectorize persistent diagram that are, in some sense, data independent. So you choose a way to vectorize a priori your persistent diagram, you get some vectors, and you do that independently of the machine learning task you have to accomplish after that, right? There are some other ways that we are going to discuss to vectorize persistent diagram that are more data-driven. So you may want, in some sense, when you see a persistent diagram, like this one, for example, it might not be completely clear which part of the diagram is of interest with respect to the task you want to do. So suppose that, for example, here, it's a kind of fake example, but you start with some time series. You get from this time series a persistent diagram, and your task, these time series are coming from some movement analysis, and you want to do some classification of movements, right? So here, you get a persistent diagram like this, and you would like to use this persistent diagram as a feature to do your classification and to distinguish between movements. And when you see this kind of diagram at first glance, it's not completely clear which part of the diagram is interesting to distinguish different kind of movement, right? So it might be interesting to try to learn, to use the knowledge you have about the problem you want to solve, to learn a vectorization which is well suited for the task you want to realize. Okay, is that clear for the idea? And this is what we are going to do, discuss today. And we are going to consider two cases. One is a supervised case, where in some sense, you have some training set and you want from some training data or from some data where you know the result of the classification, you want to find a good way to vectorize your persistent diagram. And what I'm going also to discuss in the second part of the class today is the unsupervised case. So you have some data, you do not have labels or classification results or regression results, but you use your data, the distribution of data you have, to try to learn a meaningful vectorization of persistent diagram. Okay, so to do that, there is an interesting, completely obvious remark or idea, which is that when you have a persistent diagram, this is a set of points in the plane, but you can also see it as just a discrete measure in the plane, just by saying that your persistent diagram is the sum of the Dirac measure centered on each point of the diagram. So this is a completely silly remark, but the benefit you have in doing this, first one is the space of measure, in some sense, is much nicer than the space of persistent diagram seen as set of points. Because, for example, you can sum up you can do the sum of two measures, right? You can add two measures, you can average measures, etc., etc. Okay, so if we just see persistent diagram as measure, and it's related a little bit to your remark that you made yesterday, we can do some kind of linear arithmetic sum on or barycenters of measures. Another reason why it's not a completely stupid remark is that if you remember when I presented a little bit the algebraic perspective on persistent homology and persistent modules, when I told you how we prove that a Q-tem module has a well-defined persistent diagram, is that we define, in fact, the persistent diagram as a measure on the rectangles, but intuitively, we see the persistent diagram as a measure. And just also another remark is that you have to take care that here, I do not normalize. I do not divide by the number of points. It's not a probability measure, it's just a measure. Its total mass is the number of points I have in my diagram. And one other interesting remark is that if you look at the literature, except for the case of landscape, in most cases, when you look at if you look at the literature, you will find many ways to vectorize persistent diagrams that depend on the problem people are considering, etc. So you have landscapes that are not the case, but Betty curves or distribution of birthdays or distribution of death time of your persistent diagram, etc. All this representation in general fit in a common framework and can be seen as linear representation of the persistent diagram. So what do I call a linear representation of persistent diagram? If I want to vectorize a persistent diagram, a very simple way to do that is I can choose a function defined on R2 with value in some vector space, in general Hilbert space or finite dimensional space. And thus, I can, when I have such a function, I can integrate, when I have a diagram D, I can integrate this function against the diagram seen as a measure. So, which is just, I do the sum over the point of the diagram of the value of the function at each point. Okay? And if you think a little bit about it, for example, Betty curves are linear representation of a persistent diagram. Okay? Because what you do when you do Betty curve, to each point, you associate the function which is the indicatrix of the interval, corresponding persistent interval, and then you do the sum over all these guys to get your Betty curves. If you can play with that, if you look, for example, at the distribution of the birthdays of all the beginning of your interval, persistent interval, this is a linear representation of persistent diagram. To show you another example that we mentioned also during the discussion the other day, another example of linear representation of persistent diagram are what are called persistent images. So persistent images, if you want to see them as a linear representation, you can choose a kernel K in R2, a bandwidth, which is just a 2x2 matrix. Like for example, K can be the Gaussian function. H would just be the covariance matrix for your 2D Gaussian. So you can look at this prescaled kernel, okay, with respect to the bandwidth. You can also choose optionally a function that goes from R2 to R+. In general, you choose such a, what do you call it, a weight function. So you put a weight at each point in R2. In general, you choose functions that goes to 0 when you go close to the diagonal to decrease the effect of the topological noise. For example, W can be the distance to the diagonal. And then you have when you have chosen K, H, and W, you have a linear representation of a diagram, which is just you center for each point of your diagram, you center your kernel with window size H in Pi, in point Pi. You multiply this with the weight at Pi, and you sum everything. And then you get a function defined on R2 that can be seen as an image. here I have, as I told you yesterday, I have made a transformation that map the diagonal onto the x-axis to get a squared image, okay? And for example, this is an example here, probably with a Gaussian kernel. This diagram has been converted into this image, right? And this is, so this persistent images have been introduced in a paper by Adams and co-authors a few years ago. And in fact, this is a particular case of a linear representation of persistent diagram, right? And for this, in this very specific case, they also succeeded to prove some stability results for persistent images under some assumption on the diagram they consider. But, right? Yeah. What are the? This is exactly this. This is when I write a measure against a function, you should read this is the integral of the function with respect to the measure. Sorry, it's a notation, but you can forget about this. This is just it's kind of a way of pedantic. When I say this is the integral against the measure, it's just a kind of pedantic way to say that I sum over all the points of the diagram the value of the function. Okay. So I'm not going to go deeply into this perspective of seeing persistent diagram as measure, but from this you can get some very interesting statistical property of persistent diagram seen as measure. In particular, and you have distribution of persistent diagrams. You can see them as distribution of discrete measures. And when you have distribution of discrete measure, you could look at their expectation, and in fact you can prove there are some results that tell you things about the expected measure, persistent measure that you get from this distribution, etc. You can deduce some properties of this kind of object. And this also gives a good framework to do optimization of functions that include persistent diagrams, that depend on persistent diagram. So when you do machine learning, if you want to constrain your model to satisfy some topological things that can be expressed in terms of persistent diagram, you may add in the loss of your model some function depending on the persistent diagram. And within this framework, you can prove that if your loss is not completely crazy, you can still optimize this loss using stochastic gradient descent and this kind of things. I'm not going to talk about this, but I just mentioned it. And what I'm going to talk a little bit more is about the fact that when you take this measure point of view, this gives you some ways to do data-driven vectorization of persistent diagram. So, for example, so I'm going to start with a case of supervised learning, which is, so the idea is very simple. So I'm not going to detail, there are several methods that are doing this. I just want to mention you the general idea. But when you are doing supervised learning, in some sense, you have some data, input data, called X, where you have the observation Xi and Yi is the output you want to predict. So you have a training set on which you'd already know the Y's, okay? For example, this is a classification task. And let's say that in some way to each input data point set object, you have a way to associate a persistent diagram. For example, if your Xi are time series, we have seen that yesterday that you can associate to your time series a persistent diagram, for example, doing time delay embedding, okay? So assume that whatever it is, you have a way to assign to each Xi a persistent diagram Di, and now you would like to use this Di as features together with the Xi in building a model to predict Y, the Yi, okay? So then you can choose, so you can choose a family of function defined on R2 with taking their value in some vector space, depending on some parameter theta. For example, you can say, I want to vectorize now my diagrams as persistent images, but as you have seen, persistent images depend on different parameters, a kernel, a covariance matrix, H, and a weight function. So you can take all these as parameters, and then this gives you you have many ways to convert your persistent diagram into a persistent image. In particular, in general, what you take as a parameter is the bandwidth, is the covariance matrix, okay, the H we have seen in the case of persistent image, but you don't know how to choose it. So this is where you can now use this approach we have with linear representation to say that I'm going now to consider as a new data the xy where I add the vectorization of my persistent diagram that depend on some theta. And then now when I'm going to train a model to learn the y variable, and I will see this data as a variable to optimize, and then I can write, for example, if you build a neural network, you can just add at the beginning of your neural network some layer that will take your persistent diagram as input and output the f of theta. And then when you do the optimization of your neural network, you can also optimize with respect to this parameter that you have added. And at the end, when you have finished the training, you get a model to learn y. And in this model, you have trained at the same time the parameter theta. And in some sense, you have selected the best, if you work, for example, with persistent images, the best bandwidth with respect to the problem you try to solve, which is to find the value of y. Is that clear? It's a very basic and general idea. But the fact that you can, with linear representation, you can really see some parametric families of, you can see some, you can introduce parametric families of vectorization of persistent diagram, and then try to learn the best one for your problem. So I'm not going into detail on a specific method because there is not much more than what I just told to you. But if you go through the literature, there are several implementations of this idea. For example, probably one of the first one was done by author and a co-author, where they proposed a neural network layer to learn the parameters of persistent images. Yes? You need to choose a family. For example, you say, I want to use persistent images, or I want to use landscapes, but what I want to know is at which point I will evaluate the landscape. You don't, in general, you don't take the whole function. You want to see at which part of the landscape you get something, the value of the landscape is interesting with respect to your problem, etc., etc. So in general, you are free to choose this parametric family. This is up to the user to do that, but you have to do it in such a way that after you are still able to optimize. And when you try to train your model, you need to be able to minimize something with respect to this parameter. So if you do things that are a bit crazy, you might turn into trouble to find some good parameter. Okay. Another example is what is called Persley, which was also a kind of general neural network architecture that allow to learn general representation, linear representation of persistent diagrams. So you can parameterize this architecture in such a way that whatever the linear representation you choose, persistent image, landscapes, or something else, you will get a way to find the best parameter, or you will get a network that will try to find the best parameter with respect to a given problem you want to solve. Okay? Any question about this? I don't go into detail because going into detail about one of these methods would just result in doing some kind of cooking recipe, describing some kind of cooking recipe. The only idea which is behind this is just one. Okay, and remaining are technicalities. Okay? So here we did vectorization of persistent diagram in a setting where we have some specific tasks to realize, and we have a training set for which we know the outcome, the y. So this is supervised learning. Now I'm going to move to the case of unsupervised learning, which is a case where I still have my problem of learning some variable y from some input x, but the problem is I don't have any, I don't know any of the y. I just observe the xi. I never observe the y at the time when I want vectorize my persistent diagrams. Okay, so this is an unsupervised case. And instead of doing it in abstracto, I'm going to take the excuse of a concrete application, which is time, and this corresponds to a recent work we did, or we published a few weeks ago, which comes from a concrete problem that was to detect some kind of anomalies in multivariate time series. So I'm going to describe the pipeline, and at some point in this pipeline, we will see how we do unsupervised vectorization of persistent diagram in such a way that we can solve our problem. So this is a very classical problem, detecting anomaly in time series, and a very popular one because there is a lot of data that comes as multivariate time series. So the motivation for this work was coming from some, we had some data coming from a industrial process where you have many sensors measuring some industrial process, and you want to know if something is going wrong in the way things are. And one other remark is that in general, anomaly detection is a hill-pot problem because you don't know exactly what you mean by an anomaly. It might, you have different kind of anomalies, and things that could be an anomaly in some setting may not be anomaly in other settings. So there is no universal way to do anomaly detection. It's a little bit like clustering. It's depending on what you want to do. But the idea here is to propose a persistent-based anomaly detection for this kind of data, multivariate time series. We want to detect anomaly here. I will come back on it. Not necessarily anomalies occurring on one channel of the multivariate time series, but rather we wanted to detect some big changes in the dependency structure between the different channels of the time series. So if you have, you can imagine if you monitor a sensor, a system, physical system with several sensors, the signal you get on the different sensors are in general, may or be correlated in some specific way. And what we wanted to detect is that when this correlation change a lot, we wanted to do it in a topological way. In general, what we also try to do is that we try to do things that are easy to implement, so that are effective. And at least me, when I do look at this kind of problem, I like to be able to provide a few mathematical guarantees, not to provide a kind of recipes that work on some specific case, but does not make any interesting contribution to the theoretical side. Okay, and the way we are going to do that is pretty simple. So in pink here, this is a step where we are going to talk about unsupervised vectorization of persistent diagram. But the idea is very simple. We are going to convert our time series, multivariate time series, in a time-dependent graph, in a time series of graph, taking its value in where. So we will have a sequence of graphs which are more topological objects. And we are going to use persistence to extract from this graph. So we will build some weighted graph, time-dependent weighted graph. From this weighted graph, we are going to build a filtration and get a persistent diagram that will tell us something about the topology, the kind of global topology of the dependency structure of our time series. And then we will do some unsupervised vectorization of this persistence in such a way to build a score function that will be able to detect the anomalies. Yes?
Why did you go for an unsupervised method?
Where?
Why did you choose an unsupervised method?
Because in general, I don't know exactly what an anomaly is. And I start with some data. So I will tell it again later, but the idea is that at the beginning, I only have data. And I just know that most of this data is corresponding to non-anomalous situation. There might be a few, but I don't know which one are anomalous. So I don't have access to a training set where I know that this is a normal behavior, this is a normal behavior. I don't have to decide this in advance. And it is better when you do anomaly detection because in general, you don't know how to characterize. If you know how to characterize very well what is an anomaly, in general, it's not difficult to detect. That's always a problem. Okay, so let's, it's going to be easy because we are now trained with persistent. So the way, we are going to build a weighted graph associated to our time series is the following. So we start with a multivariate time series called YT, for T going from 0 to L. And its time series has D channels, T component, okay? And now what I call, just a reminder, a graph G, a weighted graph G. This is just the data of a vertex set. V. In fact, what I'm going to implicitly do here is look at complete graphs. So I'm choose a graph V, and the functions on the pair of vertices that gives a weight to each edge. And as I'm working with non-oriented, and I want to work with a non-oriented graph, so I suppose that this function is symmetric. So in fact, my graph is just a complete graph, okay, here. And just I put weights on the edges. And now the way I associate to my multivariate time series a weighted graph is just by doing the following. I choose a bandwidth, so I look at an interval of some fixed length that will be a window size. And in this window size, I look, and I have also, I choose a stride, which is, I'm going to sample my time series by choosing some consequent windows. And I'm not going to jump by one at each time, but I can jump, the size of the jump between two consecutive windows will be parameterized with some stride that I can choose. But the idea is that when I look at my time series on a window of size delta, I just compute on this window the correlation so to weight the edge between, so now the graph I'm going to build is a graph that has as many vertices as I have dimension in my time series, and I will have one vertex for each component of my time series, okay? So each component here, you can imagine this is a tensor, and I build a graph where each vector represents one of these tensors. And now the way I'm going to weight the edge between two given sensors or two given coordinates of y is just, I look the signal on the window of size delta, and I just compute the correlation between these two signals, okay? So just the Persson correlation, right? Nothing complicated. And I weight by 1 minus this correlation, which means that if two nodes are very correlated, the weight between the two edges will be very close to 0. So in some sense, if you think as this weight as the length of the edges, two nodes will be close to each other if the corresponding signals are very correlated, and if the correlation is very, if there is no correlation between the two signals, the distance between the two nodes will be close to 1, okay? Maybe I should take an absolute value to avoid some discussion here about the sign of correlation. Okay, but in this way, I get a weighted graph that depends on the time t. Is that clear, the way I build a graph? And this, yes?
What would be take the correlation of starting at t and going to the future rather than looking at the past?
It's just, if you prefer to call this st minus delta, it's really up to you. You do whatever you want. I don't have any problem. You choose the origin of time wherever you want. It's exactly the same. It's just a way to, of course, you cannot compute this before you get to t plus delta. So it's just a choice of origin. Okay, is it clear for everybody? So we have replaced our multivariate time series by a time series of graphs, where each graph, in some sense, tell me something about the dependency structures between the different components of my time series. So now we have this weighted graph. We are going to do persistence. We are just looking, considering the Vietory strip filtration on top of this graph. So I'm not saying that what we have is a metric, but the way we do that is that we, from our graph, we build I call it the Vietory strip filtration on top of the graph, and I say that the simplex spine by the vertices V0 to Vk belongs to the rips of parameter alpha if the weight of my graph between all the pairs of vertices here are upper bounded by alpha. Okay? So it's a little bit like if it's not a metric that I'm using here because I just use the weight on the edges. So there is no triangle equality, for example. But this does not prevent me to define a Vietory strip filtration on top of it. And this is clearly a filtration. And the idea is that I'm going to connect first points that correspond to nodes that are very correlated. And then nodes that are not very that correspond to signals that are not correlated will be connected together much later. Okay, so it's a kind of natural way to build a filtration on top of such a weighted graph. And for the vertices, the zero-dimensional simplices, I just put them at as for any rips, I put them at the very beginning of the filtration. You can imagine some variant here. You could also replace the weight not by the correlation, but also by the covariance between the signal, etc. There are some flexibility. Here I choose this one. Right? And so now I can compute the persistence. So here is an example. I can compute the persistence diagram of this strip filtration. It's not a very difficult task here because in general, when you have multivariate time series, you don't have millions of channels. So you are still with an object of quite small size. And in general, we restrict to zero-dimensional or one-dimensional persistent homology. All right? So now what I have, I started from at the first glance, it does not seem like a way to simplify the problem because I started with a vector, which are time-dependent vector. I converted it into a sequence of graphs that are in some sense more complex objects, but these objects carry some topologies that tell me something about the dependency structure of my signal. And then now I associate to this graph a persistent diagram that tell me something about the way this something about these graphs, the topology of this graph. Okay. So now what I have is a sequence of persistent diagram that again I see as discrete measures. If I want, when I convert a persistent diagram as a discrete measure, I can also add, if I like, some weight in front of the each point of the persistent diagram, where the weight is a weight function. But just you can think that as this function as being one. Okay, so I just see my so now what I have is a time series of discrete measures. Okay, so I'm not going to recall you all the advantages of doing persistence, but in some sense, this persistent diagram tell me something about the structure of the graph, of this dependency graph. It can be also interpreted in some way. For example, if you look at the zero-dimensional homology, it will identify some cluster of nodes or of channels in our time series that are, in some sense, more correlated than some others. So for one-dimensional persistence is a little bit more difficult because it would correspond to some kind of cycles of correlated nodes. So, but it appears to be useful in many cases, and it's a bit more difficult to interpret. But at least if you think of the zero persistence here, you really encode the way if you have some cluster of nodes or of channels in your time series that are connected to each other and how they all connect at the very end. And it's very easy, again, from the general stability result of persistence, to prove that the way we do that is robust in the sense that if you change the weights, the weight in your graph change by no more than epsilon, then the persistent diagram that you build will not change, won't change by more than this epsilon 2. Okay, so we have a stability result. So small perturbation or small error you can make in the computation of the correlation won't change dramatically your persistent diagram. And that this is a very simple. If you take the what we have did about stability of persistence yesterday or the day before or on Tuesday, you can do that as an exercise. It's just 5 or 6 lines of proof. Okay. So now I'm with this. I started with a multivariate time series. I now have a multivariate. I have a time series of persistent diagram seen as measure. So now I want to vectorize this guy to be able to build a score function, an anomaly score detection function. And the way we are going to do that is a very simple way. So this is where we will need the data now. this is an unsupervised way, and this is just a variant of the classical K-means algorithm. I don't know if you all know the K-means algorithm, but the idea is very simple. So, and it was introduced a few years ago, and we call it the Atoll procedure. So suppose that you have a set of n discrete measures, and you can look at the average of these n discrete measures. So you just take this sum, and you may want to try to find, in some sense, the best. So you choose a k, an integer k, and you want to find a measure with k atoms that will best approximate this average measure here. This is the same as what you do when you do standard K-means algorithm. You try to find k points in the plane that best approximate, in some sense, with respect to some quadratic loss, a given set of points. And the way we do that, so we choose a number of k of point atoms, possible atoms, and we use a variant of the classical K-means algorithm. So this is an iterative algorithm. So you choose a number of steps you want to iterate your algorithm, and the idea is very simple. You start at you initialize k centers in the plane. So we are in the plane with our measure, and now, for example, you can choose them randomly from your input data. So these Ci are just points in the plane. And now, at each iteration of the algorithm, you assign to each center the set of the points that are closest to this center than to the other centers. I call these points the centers, okay? Or sometimes people call them a code book. Okay? So it's a kind of Voronoi partition of my data according to this center. And when I've done this, I just move my center to the barycenter of the set of its nearest neighbors. So this is really, it's just a measure variant because you have to take into account some weight in the measure, but this is really the standard K-means algorithm. It's a very small variant of it. Okay? So it's an iterative process. You have a k point. So suppose you have 2 points. You look at all the points that are close to the first point, all the points that are closest to the second point than the first point. This split your data into 2 sets. And now this center, each one is moved to the barycenter of its neighbors. And then now you iterate again. For this new 2 position, you look who has the nearest neighbors, and then you take the barycenter, etc. Right? And after you do that t times, and after it has been done t times, you get k points that in some sense are well positioned if you did things correctly. And if you're lucky, a bit lucky. And then now once I have these centers, the way I'm going to convert, and I will use these centers to convert my persistent diagram into a vector. So now if I have a persistent diagram, I just choose this function, which is exponential minus u squared. And what I'm going to do is I'm going to, for each center, to integrate this, so you can see it as a kernel, to integrate this kernel centered in C1, divided by some variance sigma 1 against my discrete measure, my persistent diagram. And I choose a sigma j for JS component as the minimum distance between the center j and the other point centers. Okay, so this is a completely automatic. I don't have to choose any parameter when I'm doing this. I just need some data to compute these centers or to estimate this center, and then I get a vectorization for each persistent diagram. I get a vector of dimension k that tells me how, what is the mass of my diagram around each of these centers. And this, and for example, here you have an example where on this plot you have several persistent diagrams that are superposed. The stars represent the centers that you get after doing this vectorization, and and here you get, it's come from a time series, so here you get for each of them the value of the component of the vector that evolve along the time. Okay, so you get something like that. And each here signal here correspond to what you see from one center, from each of the K center. And here the interest of this kind of the way to do the interest of doing this in this way is that we can prove some things. In particular, which is not the case we are interested in, and we proved it a few years ago, if our persistent diagrams were IID, so we're not dependent each other, were sampled in an IID way, then we can prove that when you run, so if you have n persistent diagram, if you choose t equal log n, or 2 times log n, when you run the algorithm, this K-means algorithm, what you get as the output is a good approximation of the best measure with support K that you could find to approximate the average measure associated to your distribution of diagram. Okay, where the mean measure, when I have a distribution or random variable taking its value in the space of discrete measure, can just be defined as the expectation of x is just the measure that to each Borelian set A associates the expectation of x of A, which is a real valued variable. And what you can prove, I won't go into the detail because it's quite technical, but the idea is that if you start with n observation, if you iterate log n times your atoll algorithm, what you get at the end for the centers is an almost optimal quantization of the expected measure coming from your distribution. But the problem here is that we cannot apply this case in our case where we are looking time series, because obviously, in general, we have a sequence of persistent diagrams that are not independent because we are looking at a time series. And in fact, we can generalize this result in the time-dependent case. I won't go so into the detail here, but the idea is that if we assume that the sequence of discrete measure we have is stationary with some given distribution x, so now I really look my sequence of persistent diagram, okay? If I assume also that the expectation of x satisfies some kind of technical geometric conditions that are called margin conditions, and I can get the same kind of result, but of convergence. I won't go into detail, but in some sense, to state a result of convergence, you need to understand how fast, when you sample, you get your time sequence of measures, how fast you forget about the past, how fast you become independent on what happened before. So you can formalize this in terms of what is called a beta mixing coefficient. So I just show you the formula, but I'm not going to explain it. But the idea is that this thing measure when you go jump by Q iteration in your time series, how much you forget, you are becoming independent of the past, of what happened Q times before. And using this coefficient, you can get the convergence of our algorithm. So this is the outcome, the output of our algorithm. This is the optimal quantization of the expected measure. And you see that you can, so if you choose, so you have to choose t now, not of order log n, but of order log n over q, the number of iteration, where q is such that when you look at this mixing coefficient divided by q, you want it to be smaller than 1 over n. So in some sense, depending on what you have for n, you have to choose some q that will give you this. So it is a theoretical result because in general, we don't know how it's estimating the mixing coefficient is not an easy task. And if your initialization of the algorithm is not too far in some sense that can be managed from the solution, the best, the optimal solution, then you get a rate of convergence for your algorithm. So you know that after this number of iteration, you will be at distance over for the q over n from the best you can do. Okay? So these are the guarantees you have on this unsupervised vectorization of a persistent diagram step. And now, we started from a multivariate time series. we build a time series of graphs. We get some persistent diagram from these graphs. We see this persistent diagram as measure. We vectorize them in a way where we did not know what point were anomalies or not anomalies, but we did it knowing some data. And then now we have a sequence of vectors. And now this last step is a very classical one. I have some vectors. So I have converted my diagram into vectors in RK. So I can look at this distribution of vectors. I take the mean and the covariance. I estimate the mean and the covariance of this distribution of points or vectors in RK. And then I define, so I call sigma the covariance of this distribution. And then I define a score, which is just the square norm of this vector in RK, where the metric I use is the inverse of the covariance matrix. That's very, so the idea is that if this norm is small, it means that I'm close to the average behavior of my vectors. And if it's too large, it's a good candidate to be an anomaly. And when you do that, so here you have an example of the pipeline. You start from the multivariate time series. You do the vectorization. You get, for your time series, each k component of the vectors, which is time dependent. And then here, you get the score, which is a square norm with respect to this metric in RK, which is plotted here. And on this specific example, here you have what I plotted is the ground truth. So this, I show here the places where I have anomalies in my time series. And then you see that the score here in this example detect pretty well the anomalies. Okay, is that, so this example was coming from some simulated process in which we introduce anomalies at some point. Yes?
The XI over which you computed the centroids, those are for different time steps.
Sorry, the what? So the XIs in my case are the, if you want, XT. I discretize the time. This, what I do in practice is that I start with a part or one of the time series I have in my as data, and I just have to assume that this time series, this slice of my time series does not contain too many anomalies, because otherwise, but if it corresponds to some kind of globally normal behavior, I slice it into pieces using my window size. I get a families of persistent diagrams. And then these are the XIs that I use to vectorize. And then this gives me this. In fact, I started from a time series, multivariate time series. I get another time series in dimension k, multivariate, but where the channel represents something about the topology of the dependency structure. Yeah. Okay. No, okay.
Assume that anomalies persist over some time so that we can catch them even with the discretized time.
Of course, when you go to the real applications, you have to be careful, because if you have a very sudden anomaly, which is that lasts much smaller than the window size you use, you won't detect it in the correlation matrix. So the size of the window is very important, because it's very related to the size of the anomaly you want to detect. And in practice, it might be useful to do this kind of things for different window size to be able to catch different kind of anomalies, etc. The window size is a real tricky parameter to choose in practice, because if you take it too large, you will miss some kind of very short anomalies. If you take it too small, you might miss some long-lasting anomalies, etc., etc. So, but when we start to discuss about this, we come into engineering, and that's another story. I'm not saying that this is not important and interesting work, but it's a different work.
It's like a linear trend, Gaussian noise, right? So
Sorry?
is a linear trend with Gaussian.
Yeah.
So
But it's just an illustration here. Don't worry about.
like or uniform uniformly distributed.
No, it's a case where we started with an Ornstein-Uhlenbeck process, and then we added at some specific point artificially some anomalies just to test the method in a case where we know exactly what's going on.
Like, I don't know, some noise of a particular value throughout the entire process, would it pick it out then?
I don't know. Just think about this as an illustration. I'm going to show, just to conclude, I'm going to show you just some practical example very quickly. So now when you have this score, the way you decide that you have an anomaly or not is that in fact you choose a confidence level and you build a classical statistical test and you can prove that this test is consistent. So in fact, you try to detect the scores that are too high or too low or too far from zero as anomalies, and you can calibrate your test and do that in a clean and rigorous way and prove that asymptotically when you do this kind of very classical procedure, the first type error, the error of type 1 in your test is asymptotically the correct one. But anyway, that's kind of very classical stuff people are doing for anomaly detection. Okay, I'm going to skip. I just want to show you, just because we are before running completely out of time, two kind of experiments we did, and to evaluate the experiment, because evaluating the performance of an anomaly detection method is also something which is a bit difficult. And so the way we did it in the next slide is by looking at the area under the ROC curve and the Pierre precision recall curve. So if you are not familiar with this notion, just, I don't know, maybe you all know ROC and Pierre curves. No, but the idea is that when you have a classifier, so just to illustrate, here suppose that you have, oh, we don't see my dots, but you have a classifier with two classes. So for example, the blue part corresponds to the true, so you have positive and negative class. So the blue part corresponds to the true positive. So the pink part corresponds to the true negative data point in the classification. And here what you get is that in this part, you get the points that are detected as positive and inside this ellipsoid, and outside, these are the points that are detected as negative. So for example, here you have the true positive points. Here you have the false positive point, because these are points that are detected as positive but that are negative. Here you have the true negative. So these are points that are detected as negative but they are actually negative. And here you have the false negative. So these points here outside of the ellipse, blue points, are detected as negative but they are truly positive. And when you have these four things, you can define the precision of your method to detect positive and negative, which is thus the rate or the proportion of true positive among all the points that you have identified as being positive. Okay? So if you are close to 1, this means that when you detect a positive, it's a real positive. There is a true positive rate, which is the number of true positive divided by the true positive plus the false negative. So this is the ratio of true positive points that you have actually detected as true positive, and the false positive rate is the ratio of the false positive of that is the points that are detected as positive but are actually negative among all the negative points. Okay, so and then the ROC curve is just a plot where you plot the precision. So what we do when you have a score, if you choose a threshold, you use this threshold to separate positive anomalies from non-anomalies, and then you can look at, for this threshold, what is the recall and what is the false positive rate, and then you represent this as a point here. And now if you move this threshold, you will get a curve like this, which is called the ROC curve. And you measure the area under the ROC curve because in an ideal world, what you would like to have is a curve which is close to the two sides of this square. That is, you want to have a false positive rate close to 0 and a recall close to 1, and similar with the precision recall. So the idea is that the closer you are from 1 for the area and the curve, the better you are. And then I'm going to show you just a synthetic example. I will skip because it's too late, because this one is a funny one, but it's a synthetic one, but that we have cooked in such a way that it is well suited for detecting topological change in the dependency structure. And we cooked a little bit to make it more resilient to many other existing anomaly detection methods. So what we did, in fact, is that we generated some time series using an autoregressive process of order 2, but where we were able to decide what should be the underlying dependency structure between the channels. So, for example, here we did this with a set of 40 channels, and when you look at the underlying, so before going through the autoregressive process that had a lot of noise everywhere, the dependency structure was something like a H shape, which has some specific topology. And then we, at some point here in the time series, for us, during an interval, which completely changed the dependency structure to get a different topology for the underlying graph. So we know that something happened on the topology. And then we did several sample realization of this kind of thing. And then we tried our method and we compared it to some other method. And so we compared to, is there a list of methods? Okay, so there are dozens of methods for anomaly detection for time series in the literature. So we choose a few ones that are known to work pretty well. The first 3, so this is not ABAT, it is now called TADA. So this is a method I just described, but we also use 2 other methods where we use the vectorization, but in a different way, with a random forest or with an isolation forest. So this one, for example, is a supervised method, but anyway. And then we use other methods, for example, that try to take a look at the spectral properties of the graph, some method or other existing method in the literature. And what you can see when you look at the score for these different methods, for example, for the first 3 one are topological one, are the one done with the vectorization we have done. You see that, and here is the ground truth. So you see that you detect pretty well the anomaly. If you use the spectral properties of the graph, you see that you detect the anomaly, but you also detect some fake anomalies that are not anomalies. And for the other existing methods, they do not detect anything. So it's a kind of toy example, but it's an example where it's difficult to detect the anomalies. I'm cheating a little bit here because we have generated this data in such a way to make it resilient to most of the existing methods, but easy to solve with our topological approach. But it gives some kind of interesting result. And we did the same with many benchmark data set. And I'm going to skip because it's not very interesting in itself. We observe that, as I told you, you don't have a universal way to detect anomaly. So depending on the data set, sometimes we work better or worse. But in general, in most of the cases, the method works pretty well, which means that there are many cases where detecting the anomalies on the dependency structure of the signal is meaningful. Okay, I'm running out of time, so I stop here. I thank you for your attention these 3 days.